Hello, everyone. My name is Ujjwal Gandhi, and I want to welcome you to this video walkthrough for Chapter 5.3, Advanced Vector Operations. Many of you, when you think about Earth Engine, you would think of it as a raster data processing platform, and that's largely true. But over the course of time, Earth Engine also has built very robust vector analysis capability. So in this chapter, I will be covering some techniques that you can use to visualize and analyze vector data. So we'll start with a brief overview of the chapter. We'll then cover visualizing vector data. This is something that is generally not easy or straightforward as many of you would like. So I'll cover the different techniques and different functions that allow you to create maps using vector data. We'll cover some theory and practicals. Then the next section, we'll do vector analysis. So this is your GIS-like vector analysis, where we do spatial queries and spatial join using multiple vector data together. And we'll be finishing that off. So this chapter deals with vector data, and not only the vector data that allows you to use your polygon to clip and filter your raster data, but actually analyze the vector data by themselves. So if you have a vector data that you uploaded, a shapefile to Earth Engine, or there are collections available in Earth Engine itself, how do you visualize it effectively? How do you create maps using that? And if you have two layers, how do you kind of query them together and answer some spatial analysis questions? And so we'll dive into that. And using Earth Engine enables you to do these operations, but at scale, at global scale, and using the parallel computing platform that Google Earth Engine provides. After this chapter, you'll know how to visualize vector data. If you have any feature collection in Earth Engine, you'll be able to visualize it just in a single color or multiple colors, or create maps using that. We'll cover joins. This is also a difficult topic for beginners. I'll try my best to simplify and give you an overview of how joins work and how we can join multiple vector layers together to do things like spatial queries and spatial joins. And we'll learn some geoprocessing tasks. And this will kind of allow you to do GIS-like things in Earth Engine. This is an advanced chapter, which assumes that you already know how to work with feature collections. So if you uploaded a shapefile in Earth Engine, it became a feature collection, you know how to deal with it, you know how to deal to filter using different filters available in Earth Engine. If you don't know, you can review the previous chapters. We'll also be using mapping of functions extensively in this chapter. So if you want to process each feature in a collection, you need to write a function and map that over the collection. So we'll be doing that often in this chapter. So let's start with the first section here. I'll be diving in and out of this presentation. The first one will start with visualizing vector data. So styling vector data is different than raster data. So if you have a raster data, an image, you can just say map.addLayer image, and you can give a palette if it's a single band raster, and it'll be visualized according to the min and max value that you provide, and will be rendered in those colors. If you have multi-spectral data, you can put different bands in different channels, red, green, and blue, and you can create a composite image that you can display. And that's pretty simple. Most of you would have done that already. Now, vector data is slightly different. Vector data is points, lines, and polygons. So Earth Engine and effectively any other computer system that displays the vector data is effectively rendering the vector data into an image before it can display. So if you think about a point, and it just as a coordinate, how does a point appear as a circle, for example? So that point gets rendered into an image, which appears as a circle. So in Earth Engine, you have to do that yourself. In many other GIS systems, you can drag and drop a polygon layer and it will be displayed in color. In Earth Engine, you have to explicitly render that on an image and specify the different properties. So that's how it's slightly different. But once you understand the concept, it'll become quite intuitive. So you can render vector layers so that all features of a vector layer, all lines, points, or polygons will have the same color. You can do that. Or you can render it so that each feature can have a different color based on some rule or some property that you specify. And this is essentially how you can create, say, a choropleth map, where you can give color based on some attribute value that the feature has. We'll see different functions for styling vector data. For raster data, you just say map.addLayer, right? That's the function that you have used so far. That function works for vector data as well. So you can, if you have a feature collection, you can just say map.addLayer and add it. But you can only specify one option for styling the data, and that is color. So whatever color you give, it'll be that those points, lines, polygons will be rendered in that color. If it's a polygon, it'll be having, I think, 50% transparency, and that's it. That's the only thing you can specify if you add the layer. And this is a quick, simple, easy way to visualize the data. But then if you want to have more control, you can go to the next function, which is called draw. So this function is allows you to take a feature collection and say draw this feature collection, and it allows you to specify two extra things. If it's a point layer, you can say, you can give color as well as a radius, how big the point is. If it's a line, you can also specify stroke width, which will tell you how thick the line is. And so it takes this data and renders it into according to the style. The next one is a little more complex. It's called paint. This allows you to do even more things. Particularly, it allows you to specify a different color for each feature based on a property. So this paint function takes a property and said, paint it according to this value of this property. And whatever the value of the attribute is, you'll get assigned that value. And then you can use that value, assign a palette, and they'll be rendered in different color. So this is much more powerful where you want to say, I want to render each point, line, or polygon differently based on some attribute. This is the function to use. Lastly, we have style, which has even more options, as you can see here, which allows you to say, I want to give a different symbol to each point and render them in different style, or I want to have a dashed style of the line, and so on. What it allows you to do is you can set a property of each feature saying that this particular feature has to be styled according to these options. So all of these options are customizable per feature. So this is the most powerful functions where you can set different style properties, and each feature can be styled in a completely different way. So we'll be using this also today. So let's see some examples of how the vector data styling works. As mentioned previously, you can go to this link and you'll have the code repository. We'll be working the two checkpoints in this chapter. We'll be starting to work with the checkpoint A, and we'll look at the two examples of styling vector data. The first one we'll do is we'll create this map as a population density map of San Francisco. We'll start with some polygon data, which is a census data where you have a census block and you have a population count of the block. And what we want to do is we want to style each block according to the population. And when we're creating a photoplay map like this, we want to display a rate, essentially a density population per unit area. So we'll first compute that unit area, and then we'll style each polygon according to what is the population density. So the lighter colors have less density, darker colors have higher density. So we'll see how to create this map. The workflow will be that we have this property called pop10, which is the population as per 2010 census in San Francisco. We'll take this data and we'll compute population density, which is population divided by the area of that particular block. And then we'll style each polygon using this density. We'll be using the draw function for this example. All right, so I'm going to stop the presentation and dive into code. I'll come back to this presentation and continue show the second example as well. So here we are working on this chapter F5.3, the script A. I'm going to start the script. I'm going to build the script and explain each step. So here we are starting with these three data sets. So these are all feature collections. This is a collection that is part of the Earth Engine data catalog. This is the census block from 2010. It's a feature collection, very large feature collection containing all census blocks for the entire United States. Similarly, we have the roads here, which is all the census, all the roads in the United States according along with the names as well as the road priority. Again, very, very large feature collection. I think it's one of the largest feature collections ingested into Earth Engine. I think 50 million plus features in there. And this also shows that Earth Engine can handle very large vector data, and you can actually analyze this data just as effectively as large image collections. We have this one feature collection that we uploaded from the San Francisco Open Data Portal, which is the San Francisco neighborhoods. And this will serve as geometry. This is the extent of the region that we want to create the map. So we've called the dot geometry function, which is the union of all the features. And we have got this geometry, which is of San Francisco. So let's first filter all the blocks and just for San Francisco. So we have this whole blocks layer, and we can filter it to only the blocks that fall within this geometry. And we can apply our regular filters to feature collection as well. So I'll apply the E filter bounds, and we'll filter geometry. Okay. So now we have the asset blocks. I'm just going to add it to the layer and show you what those looks like. Right. And since we're adding the map, we can specify one color that we want to specify. Maybe I'll just say red here. Okay. And we'll say this is census blocks, single color. So if you just do map.add layer, this is what you would end up with. And this will be each polygon rendered in the color that you specified with, I would believe, 50% transparency. So this works, and you have those polygons in red color. So this is good for quick visualization, and you can look at the data and get a sense of what this data looks like. But it's not a pretty map, or it's not very informative. If I inspect on any of these polygons here, you'll see that this is a feature. It's got some properties. So these are the different properties of this particular block. It's got some ID. And this is the more important one. If you want to create a population density map, we have the population of, in this block, number of people that are living in this block, and that's 125. So we can use this to actually compute the population density in this particular block and use it in our function to assign a different color to it. So now let's learn how to create a choropleth map. Right? So we'll create a choropleth map. We'll use this, we'll first compute the population density. Right? So we'll say population density is basically population divided by area. Right? So this is the formula. We want to add a new column to this feature collection, a new property called density, which contains a density. Now, how do we add a new property to each feature? How do we process each feature and do something with each feature? And that can be done by writing a function and then mapping it over the feature collection. So we'll just write this map function in line, so you can save some lines of code. And by this time, you would have already practiced writing the map functions, and you can kind of do this in line so that it can be faster. So I'll just use the same variable name. I'll say take the SF blocks and map a function. So here I can write my function. Each function can take one feature. So the input will be a feature, which I'll save it in this variable f, and it should return a feature out. So I'll take the feature, I want to do something with it. Well, this is a feature which has got all these properties. I'll extract the properties of this particular block and compute the density. So first I'll just say, what's the population? So I can just say f.get. So get is a function that allows to extract a property from a feature, and we'll just take the pop10 out of this. Right? So this will be the number of people there. We also want to compute the area, and we'll say f.area. Simple enough. In Earth Engine, whenever you use the area function, you'll always get the output in square meters. You can use population per square meters, or population per square kilometers. This is what the rest of the world uses, but in the US, the generally used unit is miles. So just to be consistent, since we are in the US here, let's say if you want to compute area in square miles. So we'll convert this square meters into square miles. Right? So how do we convert it? Well, let me just search 1 square mile in square meters. And you get this number 2.59 followed by 6 zeros. Right? So this is the conversion factor. So if I take this area and divide it by this conversion factor, you'll get the area in square miles. So we get our population, we get our area in square miles, and now we can compute the density. And this will be our population divided by area square mile. Sometimes when you are extracting numbers of properties, you may get an error that, this divide is an unknown function because Earth Engine doesn't really know what is the type of this variable. So you may have to explicitly cast this using e.number. there are newer functions in Earth Engine, such as get number. So if you know this pop10 contains a number, instead of just .get, which could be anything, text or number, if you know for sure it's number, you can just use get number, and you'll get an e.number object, which will save you some time of casting this to a number object. But you can do this as well. Right, so we have our density, and now we'll just return our feature. So we have our original feature, we did some processing, we'll set some new properties. We'll say return this with area square mile property, and that should be the area square mile. And we'll also set the density. I'll just name it pop density, and that will be our density. So now we have the feature. You can see we took the SF block function, mapped this function. Now every feature in this collection would have the new values. Let me just visualize the data after it's been processed, and I'm going to inspect polygon now. So you can see now we had 8 properties, we have 10 properties now. We computed this pop density here. So this was the population, and then we computed the area in square miles. And now we also have the population density. So you can see now we have this block where it says this block has 23,167 people per square mile of density. And we have this number for every feature in our collection. Okay. So now using this, we can apply our styling function. So before we style it, we want to know what is the range of this density. When we're styling, we need to give the min and max value for our data. So a useful function in Earth Engine is you can take any collection and run this function called Aggregate Stats. So if you type this aggregate and control space, you'll see all these functions. This aggregate stat function takes a column. So I'm going to just say, give me the stats on this population density column. And if I print this, you will get some various stats on what are the values contained in this particular column across all the features in this data. And you can see the min and max value. You can see the min value is 0. The max value is more than 500,000. So there are some blocks with very high density. The average values are about 20,000 of density. And the standard deviation is also around 25,000. So I think a good range for this data where most of the values fall, like say plus minus 1 standard deviation, it will be around 0 to, let's say, 50,000, right? So most values will be around that region. So we'll use that as a reference to style our data, and we can adjust once we have a visualization. So now we want to visualize this data. So we have SF blocks. We want to visualize it according to the value contained in the density column. And that's where our paint functions comes into play. Okay? So let's paint this. The way paint works is you create an image, we'll create a blank image, and then we'll start rendering features on top of it. So before using paint, we need an empty image. So we'll just create an empty image, e.image. And this image, we need to store values up to 50,000, right? So we saw some values are 50,000, some values are even higher. So we'll use int32 as a type of the image. So there are different types of image. It can store integers, floating points, etc. 32-bit pixel can store values up to, I don't know, a very large number. So we should be fine storing values up to 50,000. And now we can apply the paint on this. So let's say blocks paint, take the empty image and call the paint function. Okay. I'll do control space and it'll give me these parameters which I can use. So let's say what feature collection you want to paint. Let's say I want to paint SF blocks. What is the color that you want to use? And the color, instead of giving the name of the color or the value, we say the color has to be coming from pop density. Okay. So now each polygon will be rendered with the value contained in the pop density column. And so that's, you'll create an image where each pixel value is the value of this particular feature at that location. So the SF block paint is an image that we have created. And we want to visualize it. So let's just say, I want to create viz params. I'll do min 0 and max 50,000. As we just said, that this is a good range. And let's just add it to the map. So now let's say add layer, SF blocks paint. We'll just clip it to the geometry, and then we'll do this viz params, and we'll name it population density. I'm going to disable the first layer. So if the fourth parameter in the map.get layer shows you where to enable this layer by default or not. So we just not load it by default. So it's there in the layers panel, but it won't be rendered by default. So you can see once this layer loads, what's happening is each polygon is being rendered in the shades of gray, which is the density at that column. If I inspect this value, you'll see that this contains the pixel value contains a number, which is the density number that came from this column. Right? So we have now created an image, which is essentially our population density map. This is a single band image. You can see there's only one band. If you have a single band image, you can actually give a palette. You can get any palette that you like. I like to use palettes from Color Brewer. So this is a palette that I got from Color Brewer. And now if I specify a palette and render this data, instead of a grayscale value, it'll have a value going from light red to dark red. And now we have created this map of San Francisco, a population density map from the vector data. And the end result is an image. So this is an image. If you like this, you can just export this. You can say export image to Drive and export this asset blocks paint.visualize with this visualization parameters and export this. You'll get a nice rendered image that you can use in your data. Right. So this ends the first example. We'll now cover the second example.